through to 10. Now over to my left, I have a copy of the page there, so page 27 from chapter 1, Gravity. All right, so to do questions 7, 8, and 9, there is a graph here. I'm going to blow that up. There we go. So the following information applies to questions 7 through to 9. The graph shows the force on a mass of 1 kilogram as a function of its distance from the center of the Earth. Okay, we can see that graph there. So we've got force on our y-axis, and we have distance from the center of the Earth times 10 to the 6 meters, and we have a curve here. So we have a force versus distance graph. Okay, so use the graph to determine the gravitational force between the Earth and a 1 kilogram mass, 100 kilometers above the Earth's surface. Now, focus on what's actually said there, 100 kilometers above the Earth's surface. That's not a radius from the center of the Earth. That is a height. All right. So that piece of information there, the piece of information we want to find is we want to find the force. The forces are unknown. And what we're actually given is not the radius, but the height. We can work out what the height is. All right. So with the height, we can work out the radius. So let's write that down. 100 kilometers, or so 100 times 1,000 is 10 to the 5, or 1, sorry. Yep, 1.0 times 10 to the 5. It's redundant writing the 1.0, but we just stick to it as a habit. Okay, we can just 10 to the 5 would be sufficient. That is still a height. Let's just convert it to meters. All right. Now consider what we're doing here. So there is the radius of the Earth. I'm just going to pull out my data pack. Okay. The radius of the Earth equals 6.37 times 10 to the 6 meters. So you notice that, okay, we're above the radius of the Earth by 1.0 times 10 to the 5, which would basically add on another value here. It would be 6.47, but I'll demonstrate that by, now I'm working out the radius. So 6.37 times 10 to the 6 plus, we're going to add this on, but I'm going to convert it to 10 to the 6 as well. So if I times this by 10, I need to divide this by 10. So I'm writing it this way. So just to convince you, 0.1 times 10 to the 6, which would be 6.47 times 10 to the 6. Now, for the sake of the graph, we're going to take this value, let's put a unit on it, meters. There we go. Okay. So on my graph, get my mouse. All right, so distance from the center of the Earth times 10 to the 6. So I only have lines across here every half a whole million. So every 0.5 times 10 to the 6. So 6.5 times 10 to the 6, 7.0 times 10 to the 6, and so on. So the closest we've got is 6.5. What we're going to do is we're going to follow this up until when we cross over here. Then I'm going to go across. Now, if you want to, you can use pencil to kind of draw on this if it's your own book. But I'm just going to use a little a line. Let's have a look. I want a line tool. Do I have one in Paint? I haven't used Paint for a while. Yeah, there we go, line tool. So we came up this line, and I'll just go to the middle, pull that across. So the idea is we're actually a little bit, yeah, that's not really, I'm not going to use that because you might notice that my picture I've taken here is a bit skew. But anyway, if you draw this parallel to this line here, that's going to be too difficult for me to do on the computer. But you can do this for yourself with a ruler. Just draw across and you find out where it is. Now, because we've only got these lines here, the the highest resolution here, because this is 8, this is 10, the highest resolution we can actually judge when something's in the middle between these two lines. So highest resolution is actually just 1 Newton. So the closest we can actually get to approximating this is 9. So using the graph F approximately equals 9 newtons. Okay. If there was more lines on this graph, then we probably could make it a little bit more accurate, because that looks like a bit further than halfway if you take that judgment. But that's as good as we can do for that one. Now, for part B. All right, use the graph to determine the height above the Earth's surface. So pay heed to what they want and what you actually are able to find initially. Above the Earth's surface, at which a 1 kilogram mass would experience gravitational force of 5.0 newtons. Okay, so now we know the force. The force is equal to 5.0 newtons. Okay, then what we want to find is the height. Now, the way we're going to find the height, to get the radius here, we took the radius of the Earth and added the height. To get the height, we're going to have to find the radius and then subtract the radius of the Earth. So I can write it like this, just to conceptualize what I'm going to be doing in the next couple of steps. Okay, we're going to go from the graph. We have a force, and we're going to determine what the radius is, and then from that work out the height. So H equals R minus R of the Earth. Okay, as such. So from the graph, let's go find out what that is. So 5 is between 4 and 6. We follow this across. I'm going to do this very roughly. And then I'm going to go down. Okay. The radius equals 9 times 10 to the 6 minus 6.37 times 10 to the 6. With this graph, I can only get a limited, having this much significant figures isn't going to really help me here, but I'll just subtract this anyway. Okay, move out my calculator. All right, so 3, 6 point, okay, 2.36 times 10 to the 6. There we go. That plus that. Yep. Okay. All right. So that is the height in yeah, I probably accept that. I think because of the way the graph is limited, I'd round that obviously to percent figures, so I might even just write here. At really the best, because of the limitations of what we can get out of the graph, I'd say 3 significant figures is pushing. I don't know, sure if I'd mark that as wrong because of the way the question's set out, you're subtracting the radius of the Earth. But I feel that 2.6 times 10 to the 6 would be a more genuine solution that demonstrates how accurately this method can actually determine the height. So not doing a calculation, we're doing an estimation on a graph. All right, so let's have a look at some of the other questions here. So question 8. A meteor of mass 1 kilogram is speeding towards the Earth. Let's find myself some working space. Question 8. Okay, when the meteor is a distance of 9.5 times 10 to the 6 from the center of the planet, its speed is that. Determine the kinetic energy of the meteor when it is. Okay. All right, so what have we got? We have a distance that. Okay. All right, so things we need really for kinetic energy. EK equals half mv squared equals half times a mass of 1.0. Right, now be careful. For a question like this, it might even be worth your while just to write out and convert what these are. So that is not, I'm not going to put that into my V. I'm going to convert that first. So I'll substitute it out. Because it's in kilometers per second, we want it in meters per second. Now, if you travel 4 kilometers in a second, you travel 4,000 meters in a second. Okay, so that actually indicates the speed and whack. So, all right, here's the calculator. So let's punch that in. 0.5 times 1 times 4,000 squared. Okay, so we got 10 to the 3, 10 to the 6, 8 times 10 to the 6. Actually, I'll write that as 8.0 times 10 to the 6. Seems appropriate here. Okay, there's our kinetic energy. Okay, so that was part A. So we've got other information that's going to be used in parts B, C, and D. Calculate the increase in kinetic energy from the meteor as it moves from a distance of there to center of the Earth, a point there to center. And we did, okay, so we're moving from 9.5 times 10 to the 6 from the center of the Earth to a point that is 6.5 times 10 to the 6 from the center. Now, we can't just assume that this is just a change in height with a constant g, unfortunately. So we're going to have to do this in terms of energy. Now, basically, remember the work energy equivalence. So we know from work that we can determine the change of potential energy or the work done on an object by working out the area between a section and the x-axis. So we're going to be doing that in a moment. And just be reminded that part B. Okay. So work is equivalent to change in gravitational potential energy is equivalent to change in kinetic energy. So in this case, consider that we're going to be, look back at those numbers again. The increase in kinetic energy, so we're going closer to the Earth, so we're losing gravitational potential by coming closer, and we're picking up kinetic energy. So one's converted into the other. But basically, how we're going to calculate this is by using the kind of the basic concept of work, because we don't have, we could work out G, but this graph is given an F, so might as well do. Remember that work can be expressed as F times S, force times distance. Now, in this case, the force is actually changing as we go. So we're going to use the, remember, if we work out the force is our y-axis, the the distance is our x-axis, and work out an area under the curve, you can actually get the multiplier of that and you get that shape. Okay, so what we're going to do is I might just carve out that shape. So let me get the boundaries again. So we're going from 9.5 to 6.5. All right, so let me just draw that on here for the sake of what we're doing here. All right, make that thin. All right, so for the sake of the exercise, let's draw this over here. So 9.5, actually let's not use grey, let's use black. Or maybe even just use something else. We can use a bright color, which is a bright color. Okay, there we go. And the other side was 6.5. Yeah, 6.5. Okay. Okay. So we'll start by counting the squares, and we'll estimate a number of squares. So this would be the squares times square area. All right. So the number of squares is, all right, so let's have a look. We've got 1, 2, 3, 4, 5, 6 times 2 is 12. Okay, that takes us here. I'd say these two make 13. That and that makes 14, 15, 16, 17. These two make 18, 19, 19 and a bit. To make a judgment call and just go with 19 because it's less than half. I'm going to go with 19. I'm inclined to write like 19 and a half, 19 and a third, but I'm just going to go with a whole number 19. So it will actually be an underestimate. All right. So that seems to be the pattern we're doing. Just the nearest square. It's an estimation, like most of this graph work is. Okay, so let's consider the square area. So square area. All right. So running along here, each square, you've got 0.5 times 10 to the 6 on the x-axis, and going up by one square is 2. So half times 2 is 1 times 10 to the 6, and we've got that. So the estimation of the change in energy is 19 times 10 to the 6 joules, or 1.9 times 10 to the 5 joules. Now, at the start, actually, what did we count that for? That was part A. All right, so that's what it was because of the initial values. Okay, when it's there, it's traveling this fast, and it's picked up some more speed because it's picked up more kinetic energy. All right, so that we can actually calculate. That's actually the change in. Okay, that's also so that was we worked that out with work, and that's also equivalent to by this idea is change in kinetic energy. All right. Okay. So yeah, the increase in kinetic energy. Now, whenever I write change, not to confuse it with the total kinetic energy, because it is moving this with this energy, kinetic energy, and it's gained some. So this is the increase. So I use this delta symbol to symbolize change. It's not commonly used in the book, but other resources use it. Okay, so that's equivalent to the change in kinetic energy. Right. Ignoring air resistance, what's the kinetic energy of the meteor when it is there from the center of the Earth? So basically, okay, conceptually what we take is we take our initial kinetic energy and we add the change. So I'll call that EK total equals EK, that's from part A, plus delta EK, keep writing K, from part B. And then that would be just work at this. Actually, I might just do it over here. Do it the line below. Okay, 8.0 times 10 to the 6 plus 1.9 times 10 to the 5 is 8.19 times 10 to the 6, and I'll round it off 8.2 times 10 to the 6 joules. So there you go. Okay. So if I made an error in here somewhere, you can at least follow the kind of the methodology of what I'm doing. I'm pretty sure that's correct. I'm not going off any particular solutions. I'm just doing this on the fly. All right, so if I made an error, please let me know. Okay, part D. Okay, let's just adjust this. How fast is the meteor traveling when it is 6.5 times 10 to the 6? Okay, so we're solving now for V. Okay. All right, so going back to a kinetic energy formula, EK equals 1/2 mv squared. You can rearrange this by timesing by 2, dividing by m, and taking the square root. I'll just do that in steps, so if you haven't seen this before. 2 times EK equals mv. I'll swap sides and divide by m. V squared equals 2EK divided by m, and V, there we go. V equals square root of 2EK K on M. All right. So using the values we just worked out here, 2 times 8.2 E6 divided by the mass, which is 1, and take the square root of that, it's power of 0.5. Okay, so about 4, okay. I run that, I'd say we should run that to, yeah, at most 3 different figures, so I'll round it off there. Okay, that's the answer. And then that's what I'm rounding it to, so like that approximate. Okay, so 4,050 meters per second. So in fact, you only picked up 50 meters per second, but we didn't pick up a lot of energy. It was traveling very fast to begin with. Okay, so that is, I believe, question 8. So let's have a look what else we have to do. Okay, question 9. A communication satellite of mass 240 kilograms is launched from spatial orbit, 600 kilometers above the Earth's surface. The satellite travels directly away from the Earth and reaches a maximum distance of 8,000 kilometers from the center of the Earth, stopping due to the influence of Earth's gravitational field. Use the graph to estimate the kinetic energy of the satellite as it was launched. Okay, so now this is still a force graph, so just be aware of that. It's a force graph that's been designed for a mass of 1 kilogram. Okay. No, not do that. I should just get rid of the lines that way. There you go. Let's undo those. Okay. So there's orbit 600 kilometers from the Earth's surface, above the Earth's surface. Okay, we've got a few things to do with this. So let's get cracking. All right, first of all, so 9. We go from a height of 600 kilometers to 8,000. Okay, height 600 kilometers. Which, okay, I'm just going to shortcut that to 6.0 times 10 to the 1, 2, 3, 4, 5 meters. Okay. And then the radius, I would have to tack on the radius of the Earth. 6.37 times 10 to the 6 plus 6.0 times 10 to the 5. Okay, so that's the radius is. This is the initial 97 times 10 to the 6. Now I'm not going to be, I'll round that off to 7.0. I'm not going to get any better than that on the graph. Okay, the second height, again, same thing, 8,000 kilometers is equivalent to 8 times 10 to the 6. The radius is height plus the radius of the Earth. Okay, equals 8 times 10 to the 6 plus 6.37 times 10 to the 6 equals 14.37 times 10 to the 6. What can I actually do with this? No, I've read that wrong. 8,000 kilometers from the center of the Earth. I don't need to convert that. Silly me. That was never a H. That was an R. I misread that. My apologies. Okay, so cross out that. I'm doing extra work for no good reason. I might even edit that out. Okay, so moving on. Use the graph to estimate the kinetic energy of the site was launched. Okay, so then we've got our boundaries. We've got from 7 to 8. Let's have a look. In terms of that, okay, from 7 to 8, so let's put in some markers for those. Okay, not eraser. Let's use my tool. Thank you. All right, 7 to 8. I'm going to say that's 1 square. These two combine as 1 square. 2, 3, 4, 5, 6, 7. Okay, so the area enclosed equals 7 squares. So then and just a reminder, this is for mass equals 0.1 kilograms. Keep that in mind. Okay, area enclosed 7 squares. And that's 7 times, all right, each square is 0.5 times 10 to the 6 on the x and 2 newtons on the y. So approximately 7 times 10 to the 6 joules. Okay. Now, again, I'll remind you that is for 1 kilogram. Now, you could actually go through and convert that to G and say, okay, well, force divided by mass give you gravitational acceleration, and then consider it that way. You can even rescale the graph using that. So essentially, you could just go, okay. Well, for all intents and purposes, that is actually the case, because if I divide this by 1, so force A or G in this case, F divided by M. If I divide 2 by 1, I get 1. 4 by 1, I get 1. So you can almost replace this with G. It just happens to work out nicely. Now, let's say, for example, that wasn't the case. So this is actually, yeah, it's a correct answer for 1 kilogram. But let's just remember our kinetic energy formula. So even if that wasn't the case, if I couldn't convert that nicely, I can just scale up by looking at the multiples, because EK is equal to half mv squared. Okay, so that implies, because m is there in the formula and you just go constant times m times v squared, E is directly proportional to m. So I'll write that. EK is proportional to m. Now, so m is increased. So going back to our satellite. All right, our satellite is 240 kilograms. So times 240, so it's 200. So we multiply 1 by 240 to get it to 240 kilograms. Now that would imply, if m times by 240 leads to energy kinetic times by 240. So the new kinetic energy for m equals 240 kilograms, EK equals 240. Can't see that, sorry. There we go. That's by working so far. So 240 times by 7 times 10 to the 6. And let's calculate time. Let's calculate out. Okay. So 7 times 240 is 6. Okay. All right. And that's a lot of zeros. Okay, so that's 3, 6, 9. 1.68 times 10 to the 9 And because it's really you only can work in decision figures for this, so I'll say 1.7 times 10 to the 6 joules. Hopefully I'm not too far off. Okay. All right, so that was question 9. It wasn't actually as complicated as I thought, because they changed from a height, so you go from a height to a radius. It was interesting. I was thinking when I calculated that large number, I was actually off the graph. I realized I made a mistake. Okay, so let's do question 10. Let's move over, get some more space. Okay, question 10. All right. So in question 10, a 20-ton remote sensing satellite in a circular orbit around Earth at an altitude, again, that's height of 600 kilometers. The satellite is moved in new stable orbit altitude. So again, that's a height. So this one is going from height to height. Okay. All right. So just in the previous question, we've already actually gone, okay, height of 600 kilometers. I'm going to get lazy here just for the purpose of actually already calculated this already. Radius, so that's height 1, radius 1. We've actually done 600 kilometers of height. That gets you approximately 7.0 times 10 to the 6 meters of radius. Okay, so we did that in question 9 over here. Okay, now I have to do the second one though. H2 equals 2,600. Really, it's just adding on. Look, I'll do it anyway. Okay, commas. Okay, that's equivalent to 1.6 times. Okay, so we've got 1, 2, 3 commas. Okay, so that's 10 to the 6. Okay, radius 2 equals height 2 plus, oopsies, plus the radius of the Earth. Add those on. Okay, 2.6 times 10 to the 6 plus 6.37 times 10 to the 6. Okay, second value, 8, very close. I'm just going to round that to 9.0 times 10 to the 6 meters. Let's get all our nice little units and all that's in a row. There we go. So we're going 7 to 9. And we've got a new graph. That looks good. Use the following graph to estimate the increase in gravitational potential energy of the satellite as it moved in its low orbit. Now, this one is in gravitational field strength, so be careful. Okay, so if you think about the formula, now it's again, it's mgh but we have a g graph on our y, so we've got g on our y-axis and distance on our x-axis. So if I think about it in terms of mgh, yeah, and g is not consistent throughout. It changes in a curved fashion, but okay. For this exercise, this section is the area enclosed. Okay, so then I have to multiply by the mass. All right, so think of it this way. Okay, so I'll just break up that concept a bit further. Line below, mass times number of squares. Okay, maybe I'll just draw that out. Okay, wrong mouse. Let's get my line tool again. Okay, so we're going from 7 to 9. There's 7. And there is 9. All right. All right. So 1, 2, 3, 4. 1, 2, 3, 4, 5. That's 20 enclosed in there. 21, 22, 23, 24, 25, roughly. Yeah, I'm going to go with 25. I'm going to stick with whole numbers for this. And I'm doing guesstimation, so we have kind of that's in this bracket. So 25 squares times by. Okay, so you're going, yeah, it's 0.5. It's actually no. This one's actually going up by 1. It's 1. So we're going up by G, which is newtons per kilo. So I might even just show you this way. I'm going to do newtons per kilogram. So each square, so what I'm writing here is each square. So 1 Newton per kilogram times by okay, the x-axis is 0.5. I usually write that one first. 0.5 times 10 to the 6 meters. There we go. So bring that across. That's what I'm doing. Okay. So 25 squares of that. Let's put another close bracket around that. And now meters times newtons is joules from the work function. So newtons meters is joules divided by kilograms. And the kilograms will be in here. So you see all these units cancel out. So for the sake of demonstrating that this works, I'm including the units in here. Okay, so we're just going to simplify that a bit. I will substitute in the mass. If I go back to the question, go back here. Question 10 is 20 tons, sorry, not 200. 220, let's write that is 20,000 for the sake of this, times 25 squares. So squares is not a unit, it's just what we're counting. So 25 of, I can still do that. Okay, so we've got, this becomes 0.5. So that's really 5 times 10 to the 5. Newtons times meters is joules, so joules per kilo. And the kilos are from here, so the kilos would cancel, and that's how we'd end up with a unit of joules. All right, so let's just put the rest of that in the calculator. So 20,000 times 25 times 5e5. Okay, so this is now 2.5 times 10 to the 11. Okay, that's significantly larger, but this is a significantly larger object. That's why, so don't get too scared. It's basically, we just scaled this up by a lot more mass, and we're doing problem solving with things that were in previous questions, like these ones in 1 kilogram and then 240 kilograms. And then we've basically gone from 20 metric tons, which is a few orders of magnitude larger as well. So that's why we're getting 10 to the 11 for our answers now instead of much smaller values. Okay, so there we go. That's question 10. I don't have the resources to double check all these answers, but I'm pretty confident with my method. If there's any mistakes in the method, please let me know and I will correct it in due course. All right, thank you guys.